Hello scholars, welcome back. We're looking today at symmetry. What do we mean when we say that a shape has symmetry, and can shapes have more than one line of symmetry? So let's look at the definition. When a shape has symmetry, we say that it is symmetrical about a central line. So in other words, we can draw a line or make a fold that forms an imaginary line through that shape and divide it into equal parts. That's basically what we're saying. And a shape can have more than one lines of symmetry. So we're saying some shapes we are able to fold them over themselves more than one places, in more than one places, and they will fit exactly over themselves. You won't see any edges coming off or any lines or spaces. Once you fold it along that line of symmetry, or cut it along that line of symmetry, you can fit the two pieces that are formed, you can fit them over each other. So this line that we are able to draw halfway through in any direction, because remember we're saying some objects can have more than one line of symmetry. This line is called the line of symmetry. We're able to fold the shape exactly over itself along that line. Many shapes have more than one lines of symmetry. A circle has infinite symmetry. So what we're saying, for the circle, we are able to draw the diameter, the line that cuts the circle into halves, into two equal parts. We can draw the diameter along in any direction, infinite possibilities for the diameter of the circle, right? Many lines of symmetry, because if we look at the circle, right, so we can fold it over itself. See, we can fold it and it fits exactly over itself. So this line in the middle, this fold that we created in the middle, that is a line of symmetry. We can fold it this way. We can fold it infinite ways. Infinite ways we can fold the circle over itself, right? So once it's a perfect circle, you should be able to fold it over itself no matter which orientation. No matter the orientation, you should be able to fold it and it fits over itself. And each of the folds is called the diameter, because it is the line that cuts the circle in halves, in two equal parts. So the line of symmetry in a circle is actually the diameter of that circle, right? Halfway across the circle. So let's look at the square. So this is a square, and we know that in a square we have four equal parts, four equal lengths, right? So we know we can fold it this way. So we can fold it that way. That's one line of symmetry there. We can also fold it the other way, vertically, whichever way you want to call it, vertically, horizontally, in a square is the same, because the lengths are the same, right? So we have that. Can we fold it diagonally? If we fold it along the vertices in the square, does it fit over itself? Well, here it is. I folded it along the diagonal, and I can fold it along the other diagonal. Okay, it fits over itself. So the square then has, how many lines of symmetry does the square have then? We're able to fold it and get a square. Make sure the lengths are the same. Get a square and see. We were able to do it 4 times. See if you're able to fold the square any other way, any other number of times, and get it to fit exactly over itself. So we were able to fold it horizontally, vertically, and the 2 diagonals, we were able to fold it over itself. So we see that the square has 4 lines of symmetry at least. You can check, do your own check and see if you find any more. How about the rectangle? So this is a rectangle. The length is different from the width. So we're able to fold it vertically over itself. Okay, we'll fold it vertically over itself, so that's a line of symmetry there in the middle. We can fold it horizontally over itself. So see, it fits exactly over the 2 halves, right? They fit. Can we fold the diagonals of the rectangle the way we did for the square? So if we start to fold the corners at the vertices, what happens with the rectangle? See what happens? It's not able to go all the way to the other diagonal. And if we try starting from that one or one of the other 2, it's the same thing. It doesn't fit nicely over itself the way the square did when we folded the square along its diagonal. So the rectangle seems to have only 2 lines of symmetry. Get a rectangle and try for yourself and see if you can find any other way of folding it other than horizontally and vertically. Other than those 2 ways, see if you can find any other way to fold the rectangle so that it fits exactly over itself. Based on our experiment, it seems to have only 2 ways, and the square has 4 lines of symmetry. Alright, so let's look at these shapes and see how many lines of symmetry we can identify. So we know for the rectangle we can't draw the diagonals. They are not symmetrical. Right? We know we could cut it this way. So that's 1. And we know we could have also cut it that way and it would have folded over itself. We just did that, right? With the square, we were able to do it vertically. We were able to do it horizontally over itself. We were able to do the diagonals and they fit over each other. So as far as we know for the square, based on our experiment, for the square, it seems to have 4 lines of symmetry. How about this shape? If we cut it this way, then we're going to have this point sticking out up here. Maybe these 2 might fit over each other, but this point is longer than this one. So if we fold it along the horizontal line, it's not going to be symmetrical. I think we could fold it this way though, and get them to fit that way, right? So that will have 1 line. For this one, same thing. I think we can fold it there. Because if we try to fold it horizontally, these are much bigger than these. So they're going to stick out at the top. You see what I'm saying? So this seems to have 1 as well. We just saw that the circle has countless lines of symmetry. Okay? So we're going, for the circle, we're going to say it as countless or infinite symmetry. For the triangle, It depends on the type of triangle, right? For this triangle here, we seem to be able to cut it that way. If it's a scalene triangle, we definitely will not be able to have a line of symmetry because it has different lengths of the side. For the isosceles, we can definitely have one line of symmetry. For the equilateral triangle, we will have more lines. This shape it's irregular, so it has no symmetry. This shape here has no symmetry. There's no way that we can cut it or fold it to make it fit exactly over itself, right? There's no way that we can do it. So this has no line of symmetry. Let's look at these letters of the alphabet. And of course, it's going to depend on how you write your letters, how perfectly you make your letters. But imagine they are perfect letters. So we could cut the C like that. So it would have one line of symmetry. The D, if it's a perfect D, we could cut it that way and it would fold over itself. We can't cut it lengthways, neither for the C. We could cut the B this way, fold it over itself. Some people write their B with a smaller thing at the top. So if that's the case, we would not be able to make it symmetrical. So it depends on how you write your B. For the A, we could not go horizontally. It would not be symmetrical. But we could go vertically and get. You see that? We could cut it vertically and it would fold over itself. How about the E, the capital E? I'm thinking if we go like this, it will be symmetrical. Definitely we can't do that for the F because it's just shaped. The way it's shaped, we can't cut it to make it fit over itself. The X, yes we can. We can go vertically, and depending on how you write your X, if they are the same, we could also go this way. It depends. We write our X's differently. For the G, we can't. There's no way we can fold or cut the G to make it fold over on itself exactly, right? So guys, when we talk about a shape being symmetrical about a line, we simply mean we are able to draw a line halfway and fold the shape over itself. Or if we cut out the outline of the shape, we're able to fold it and it fits neatly over itself. In other words, the two pieces are congruent. They are identical. They can fit over each other. Some shapes have many lines of symmetry. Some have one, some have two, some have countless lines of symmetry. We're able to fold them many ways, right, depending on how they are presented. So that's it for symmetry. That's all there really is for symmetry, right guys? If you have benefited from the video, just drop a line to say thank you, miss, for your efforts. I would appreciate that encouragement. I would appreciate if you would share the video so other students may benefit. And please subscribe if you haven't done so before already. And if you want me to do a video on any particular topic, just let me know and I'll gladly do that for you. So take care, my scholars. I'll see you in the next video.